All right, we're going to start today's material, and as a reminder, this is all Chapter 7, so it's not going to be on the upcoming exam, but still will be covered on the third exam and the final. Speaking of exams, just one last reminder about the exam review, which is going to be Friday, 2 doors down at 2 p.m. So it's all right, so that's the same information as last time, and I'll see some of you there. All right, so we're going to continue on with where we left off last time and hopefully make it a little bit more relevant to chemistry today and less physics-like. So the key thing we learned last time was that the change in internal energy for a system is equal to Q plus W, where Q is the heat and W is the work. So we're always talking about transfer of energy between the system and the surroundings. You never just create or destroy energy. And the only two ways you can do that are with heat, which is thermal energy. That's when two things have different temperatures and they transfer that energy in that way, or work, which is usually associated with motion, forces, things like that. In chemistry, in most cases, the work term is pretty ill-defined, I would say, for most chemical systems. We're only going to talk about in this class one specific situation when you can calculate work very easily. Other situations that are similar to this would require calculus, which we don't assume that you guys already have. And in other systems that are totally different, it's not really straightforward how to do this. So we're going to actually see today why we typically avoid the work term altogether. But we'll talk about it in one context, which is called expansion work. So basically in expansion work, what you're doing is you have a gas that's either expanding against a constant pressure or being compressed by a constant pressure. And we haven't learned about gases yet, so that may not be totally intuitive yet. But basically when we talk about pressure, it's equal to force divided by area. So we're going to define pressure and talk about it a lot more in Chapter 8. So it always feels a little bit weird to introduce this now before we've talked about gases, but 7 and 8 are all in the same exam anyway. So by the time we get through both of these chapters, this will all make perfect sense, I hope. And so the units for pressure are a lot of different things. There's SI units that would be called pascals, but in most cases in chemistry, we're using a unit called atmosphere, where 1 atmosphere is the average pressure at sea level of the air on Earth. All right, and then the equation that allows us to calculate expansion work when a gas is either expanding against a constant pressure or being compressed is going to be pretty simple. It's going to be, there's a minus sign out front. That's the one that people often forget is the minus sign, but it's the negative of the external pressure. So again, the external pressure is the pressure that's either that the gas is pushing against as it expands, or the pressure that's pushing on the gas if it's compressing the gas. It's that external pressure times the change in volume, delta V. All right. Now, most often, so let's define the terms here real quickly. So again, P external, P-E-X-T, is a constant external pressure. So we can only use this equation when the external pressure is constant, and that's the only situation we'll actually talk about in this class anyway. But it does require that the external pressure be constant and not changing. And then delta V, as we said, is change in volume. And as we already talked about last time, delta always means final minus initial, so it's the final volume of the gas minus the volume that it started at, the initial volume. So those are the only two terms you need to calculate expansion work. Now the units in this are a little bit weird because what we normally have is pressure in atmospheres and volume in liters, and so if you multiply those two together, you have atmospheres times liters, which is a weird unit for energy or work. So we don't really often leave it in that form. So a conversion factor that you're going to be aware of is that 1 atmosphere liter, again when you just multiply these two together in their typical units, is equal to 101.3 joules. So we haven't talked about joules a lot, but joules is the standard SI unit for energy or heat or work, whatever context you're talking about it in. So we'll use joules pretty much exclusively in a chemistry context. So that's the conversion between those two. So then if we think about the signs that are possible, again, we have this minus sign out front. Delta V can be positive or negative. External pressure is always a positive number. So if you're expanding the gas, that means your final volume is bigger than your initial volume. So that's a situation where the gas expands. And that means delta V is positive, greater than 0, which means from this equation up here, because there's the minus sign out front, that would mean a negative work. And as we talked about last time, when work is negative, that means work is being done by the system. So when a gas expands, where the gas is your system that you're focusing on, it's doing work. So work done by the system whenever you have expansion, positive delta V. All right, and then the other situation is just the exact opposite of that. If we're compressing a gas, that means the final volume is smaller than the initial. One of these days I'll change that battery, but not today. All right, so if the final volume is smaller than the initial volume, that means the gas is compressed, is the terminology we would use. It's going to be the opposite situation in terms of the signs. Negative delta V, volume's getting smaller, positive W, and whenever work is positive, that means that work is being done on the system. So when you compress a gas, you're doing work on the gas. So at this point, we just have two simple equations to work with. Delta E is Q plus W. If you know both of those, add them together. Just pay attention to the signs like we talked about last time. And now we also have one situation where we can actually calculate W. So if you're going to calculate delta E, you need to know Q and W, and this is how you would get work in the specific situation of a gas expanding. So let's just do like one, simple example problem. So we have a reaction at constant temperature produces an ideal gas. We'll talk more about what ideal means in the next chapter, but it's just a gas. And the volume expands from 1 to 10 liters against a constant pressure of 0.978 atmospheres. Calculate the work done. All right, so this is the situation. Usually when you're, when you're studying expansion or compression of gases, you have a container that has sort of a movable lid. So like a lid that can move up and down as the gas is either expanding, or if you're going to compress the gas, you press against that to compress it. So that's kind of what this little cartoon is showing. So constant pressure of 0.978 atmospheres pushing down on the gas, but then it expands from 1 to 10 liters during this process. We want to know what is the work associated with that process. So the only way we can calculate work is with that simple equation, negative P external delta V. And so all we have to do is just put in the terms that we need. So external pressure is 0.978 atmospheres given to us directly in the problem. And then for delta V, we have to do final minus initial. So the final volume is 10 liters. That's where we end up. The initial volume is 1.0 liters, and so the difference is 9.0 liters. I guess I had one more decimal place in the answer in the question, but it's all right. I'm not going to change the number. All right, so that's delta V, 9 liters plus 9. And so then when we do this, we get minus 8.80 liter atmospheres. Now, I suppose, and that means the system is doing work because the sign is negative. There are situations where we might just ask you to leave the answer in liter atmospheres. So again, look closely at what the question is asking, look at the answer choices if it's multiple choice. So this would be a valid answer since I didn't specify units here, although most commonly we're going to want this number in joules, the standard unit for work or energy. So if we want to convert that to joules, you have to remember the conversion factor we just introduced. Minus 8.80 liter atmospheres. And then the conversion is 101.3 joules in 1 liter atmosphere. So in joules, this would be minus 891. So either of those is technically a correct answer, but if we specify units, make sure you do that correctly. Sometimes people wonder, well, how do I remember this conversion factor here? So there's actually a way to remember it from your periodic table that we give you. So let's take a look at that real quick. Okay, so let's zoom in on these constants down here. All right, so you guys, we're going to talk about these constants more as we go through these next two chapters, especially chapter 8. But there's this constant here called the universal gas constant R. We don't need to know what it means yet, but notice that it would give you two values. One of them is in joules, one of them is in liter atmospheres. So if you divide those two, that'll give you that 1 and 1.3 number. So if you forget it, just divide the two values of R, which one of them is in joules, one of them is liter atmospheres, and that'll give you the relationship between those two units. So if you forget that, that's the way to come back to it and remember it. All right, just a little hack that I thought I should tell you. All right, so that's going to be all we really have to do about work. Expansion work against a constant pressure, one pretty simple situation. Now the reality, though, is what we're mostly interested in for chemical systems is the total change in energy, delta E, which we've introduced as being the sum of heat and work. So in reality, if we want to find delta E, we need both of those, and that's not always particularly convenient to do. As we'll talk about, measuring Q, the heat term, is actually relatively straightforward in most cases. But measuring work, it's easy if you have this specific situation here, gas expanding against a constant pressure, but there's a lot of other physical changes and chemical processes that would not involve this situation, so what do we do at work there? Well, the reality is what we're going to actually end up doing is introduce a new state function called enthalpy. And the reason is that because most reactions in a lab setting, an experimental chemistry setting, are done at a constant pressure, the reality is you'd have to calculate Q and W to do delta E. It's not always easy to do that. It requires two separate measurements. So delta E is not particularly convenient state function for us to use. So we're going to introduce a different one that's a little bit better to work with. So we're going to start with the definition of delta E, which is Q plus W. And as we talked about, if we're at constant pressure, which we usually are in a chemistry setting, then work is negative P external delta V. We also just introduced that, and we can write that more simply as just minus P delta V. Because if we're only dealing with one pressure, it doesn't matter if we define it as external or internal. It's the constant pressure P that we're dealing with. And then what we're also going to say is we're going to measure the heat at constant pressure. And there's no different definition of this. We're just going to abbreviate it as Q sub P, meaning heat measured at constant pressure. That's all that QP means. So what we can say then is if we're at constant pressure, delta E is equal to the heat measured at constant pressure, QP, and then we're going to replace W with minus P delta V. Just do a little bit of substitution here. So this is another way to write delta E at constant pressure. And so then what we can do is we can solve for QP, because Q, as we'll talk about today, is pretty easy to measure. It's just based on temperature changes and a few other terms, but that are all easy to get to. So Q, we're going to isolate and solve for that. QP is equal to delta E plus P delta V. And so this parameter here, QP, is a sum of two state functions. Delta E is a state function, anything that has a delta in front of it. P delta V is a state function because it's a constant pressure multiplied by a state function delta V. And so if you have a sum of two state functions, then the result is also a state function, as it turns out. So we're not going to call it QP, we're going to call it a new state function delta H, which is enthalpy. And so put more simply, the state function delta H is equal to the heat measured at constant pressure. So if we do a chemical reaction or a physical process, whatever the case is, at constant pressure, we measure the heat, that directly gives us this new state function delta H. And so it's a little bit easier to deal with because it's only one term. And so again, H here is what we call enthalpy. And in absolute terms, it's E plus PV. And then, of course, we put the deltas in front if we're talking about change in enthalpy. All right, and so the significance of this is that delta H is a new state function, and you can measure it or calculate it just by measuring or calculating the heat of a process at constant pressure. So we don't have to worry about heat and work when we're measuring delta H. We just have to measure heat. It has to be at constant pressure for this to work. It's only true if it's a constant pressure process, but most processes are in chemistry, or at least can be controlled to be constant pressure. And so then we're able to just measure delta H in that way. So that's our new state function, change in enthalpy, delta H, that we're going to be dealing with a lot in chemistry. Now you might think that this is a little bit unsatisfying. So like, well, you told me delta E was really important. It's the total internal energy change. And now we're going to just replace it with delta H, and that seems kind of, kind of sketchy to me. Well, let's talk about then the relationship between delta H and delta E, and kind of hopefully convince you that these two really aren't that different from each other. So even though they have precise definitions that are different, in reality the values that we measure are usually going to be similar, and they're going to tell us very similar things. So going back to that definition of delta H related to delta E, if we talk about different situations in chemistry that can occur, so let's say we do a reaction that does not involve a gas. Pretty much all the reactions we talked about in chapter 6 would have been that category, aqueous solutions or things like that. Well, the reality is that we're going to talk more about gases in chapter 8, but gases are the ones that have really big volumes, or really big changes in volumes whenever something happens to them. If you're doing something in a liquid state or in solution, the changes in volume are typically minuscule compared to the volume of the system. So in a solution or anything that doesn't involve a gas, your delta V term is very small. So you'll usually have very small volume changes if you're talking about something that's not involving a gas, liquids or solids primarily, or dissolved materials in solution. So when you have very small volume changes, this P delta V term is basically equal to 0. And that means in this situation, because this goes to 0 here, delta H is practically the same as delta E. Within the error of the measurement, they would be identical most likely. So in many situations, even though it's technically defined differently and you're measuring it just as the heat term, in reality, delta H and delta E are very close to each other in terms of their magnitude, in terms of what they tell you. And then even if you have a gas phase reaction, but the moles of gas does not change between reactants and products, let's talk about this one here. So as an example, let's say we're combining hydrogen and chlorine gas, H2 and Cl2, to make HCl gas. So no solution here, everything's in the gas phase, which again, chapter 8 is where we're going to talk about that a lot more. In this situation, if you look at the reaction here, on the left side of the arrow, the reactant side, we have 2 moles of gas, 1 mole of H2, 1 mole of Cl2. On the product side, we also have 2 moles of gas, 2 moles of HCl. So as we'll talk about more in chapter 8, if the moles of gas is staying the same and the pressure is staying the same, it's constant pressure, the volume is also staying the same. So in this situation where you have the same numbers of moles of gas at the beginning and the end of the process, this P delta V term is exactly equal to 0. The only time you can have a non-zero P delta V for gas phase processes is if there's gas being generated or gas being consumed. And so that means this delta H would be equal to delta E. So even though this is a gas phase reaction, this is another one where those two are actually exactly equal in this case. Now there are going to be some reactions or some processes where the moles of gas does change. So it could be a chemical reaction, or it could be a physical process where you're converting a liquid to a gas, where you're generating gas during that process. So if we have this chemical reaction here, the combustion of carbon monoxide to make CO2, we don't really need to worry about the sort of numerical implications of this, because we haven't gotten all these relationships yet. But we see in this reaction here, we have 3 moles of gas on the reactant side, 2 COs, 1 O2, that's a total of 3. On the product side, we're forming 2 moles of gas. So the number of moles of gas is changing between reactants and products, between the start and the end point. So in that situation, when the moles of gas is changing, this P delta V term will not be equal to 0. Again, we're not going to calculate this numerically and talk about these differences quantitatively, but because this P delta V term is non-zero, that means these two would not be equal. So this is really the only situation where they're going to be significantly different from each other. But that said, in most cases, it's not exclusively true, it depends on the situation, but in most cases the P delta V term is a lot smaller than the heat, QP. So still, even in these situations, they're not going to be that different from each other. They might differ by a few kilojoules or so, but they're not going to be like totally off, so not exactly the same. So the long story short is that delta H gives us a lot of the same information. Numerically, it's usually very similar as delta E for a chemical reaction, especially if it doesn't involve gases, and it's just more convenient because it only requires us to measure heat and not to consider the work. So in a lot of, we'll try to be precise about it in this class because we want you to know the difference between delta H and delta E from a definition standpoint. But in a lot of situations in chemistry, delta H and delta E are almost used interchangeably. They mean different things, but They're measured as heat typically, and for most processes, numerically, they're almost the same as each other or even identical. So this just gives you a rundown of the different situations, and really, in all of these, it's very common for delta H and delta E to be similar. This last one here is the only time when they could be very different, but that depends on the relative magnitude of P delta V. Usually it's smaller than the heat term anyway, so it's not going to matter that much, but that's situation dependent. All right, so we just want you to be aware that that's the difference between them and why we kind of abruptly moved from delta E to delta H, but in reality we're not really talking about vastly different things. All right, so once we are able to calculate or measure delta H, there's two possible situations here. So there's exothermic and endothermic. So in an exothermic process, the heat, which is equal to delta H at constant pressure, is going to be negative. And so what we think about in this case is that whatever process is happening, if it's a chemical reaction or a physical process, heat is released as a product. Now, it's not really a product per se. It's not, heat is not a form of matter, as we know. So I'm going to put that in quotes because it's not really a substance. But what you can think about it, or the way you can sort of visualize it, is let's say we do an exothermic reaction. So the classic example of an exothermic reaction is burning something. I mean, if you burn something, you're producing the fire, and the fire is releasing all kinds of heat. So anything that involves combustion is going to be exothermic. So if we combust hydrogen, which is fairly dangerous, as the passengers of the Hindenburg would tell you, but nonetheless is very exothermic and has a negative delta H. What we can think about in this case is that heat is produced as a product of the reaction. Even though it's not rigorously chemically true to say that, that's how we would kind of visualize it. Heat is being released as the reaction progresses. And what then happens is the temperature of the surroundings increases. So whenever you have an exothermic process, it gives off heat to the surroundings, and so the temperature of the surroundings increases. If you're standing next to a fire, you know that, of course, to be true. Now, most of you here are probably, from Houston area or Texas, so you may not know. Does anybody know what this thing is here? Hand warmers. So some of you are familiar. So I used to use these all the time when I had a part-time job in college at the Symphony Hall, and I had to stand by the garage entrance, and it was in Cleveland, so it was like freezing there. And I had hand warmers the whole time to stop myself from getting hypothermia. But anyway, these things are an example of an exothermic reaction. Basically it's a controlled rusting of iron that releases heat. And so it's an exothermic process, and that's why the whole thing warms up and keeps your hand warm if you're holding it. Now the opposite is endothermic. These are actually not as common, I would say, but there are some common examples of them. And so this is just when your delta H is positive. And so in an endothermic process, endo means into, if you're a Latin scholar. I think there's Latin, but anyway, it means heat is absorbed during the process. And you can then think of the heat as a reactant, again in quotes because it's not a substance, but it's going into the reaction to make it happen. So these aren't as common, but one that's used in these cold packs, the opposite of a heat pack, a cold pack, it's not usually a chemical reaction that happens inside this. So this is one where you you break something and it usually inside of there and it kind of gets cold. This often involves either dissolving something in water or precipitating something from water. Those are kind of the two ways that these cold packs work, where there's requires heat for that to happen. So anyway, like one example, I don't think they use these in these exact types of cold compresses, but if you take ammonium nitrate, pretty simple ionic compound, if you dissolve it in water, what you'll notice is that the water gets colder, and that's basically because it's an endothermic process. Heat has to go into this to happen. So when you dissolve ammonium nitrate in water, you have to put heat into it to prepare the aqueous solution for it to dissolve and form aqueous ammonium nitrate. A lot of ammonium salts are like this for whatever reason, but ammonium nitrate's particularly relevant example. So if you dissolve ammonium nitrate in water, and if this is a pretty simple experiment to do, you'll notice that the water gets cold because heat is going into the system as the ammonium nitrate dissolves. So when you have an endothermic process, the temperature of the surroundings gets colder, they decrease. All right, so that's kind of some conceptual background information about enthalpy. But what we're working towards is how to actually calculate enthalpy. We'll get a little bit of background on how you measure it, of course, but this is not a lab class, so you're not going to actually do that. But if we're thinking about a chemical reaction, let's give sort of one last conceptual look at how this works. So if you have an exothermic reaction, this means delta H is negative, less than 0. Now, as we talked about, anytime you have a state function with delta in front of it, that means final minus initial. So if your delta H is less than 0, that means your final enthalpy has to be smaller than your initial enthalpy. You're subtracting a bigger number from a smaller number, and that gives you a negative number out of it, final minus initial. So when you're doing a chemical reaction, the initial state is going to be your reactants, and your final state is going to be the products. So if you have an exothermic reaction, what this means is that the products have lower enthalpy than the reactants. The enthalpy is decreasing during the reaction. All right, and so because you have less enthalpy in the products, you're giving off that extra energy as heat, and that's why the temperature of the surroundings increases. I'll write that again here, delta H less than 0. So in an exothermic process, we don't usually measure absolute enthalpy, but that's in reality what's happening when you have an exothermic reaction. The reactants have higher enthalpy than the products, and so the difference between products and reactants is a negative number, a smaller number minus a bigger number, final minus initial. Then the opposite is true for endothermic, where delta H is positive. So if final minus initial is positive, that means the final state, the products, have higher enthalpy than the reactants. And so in order for this enthalpy to increase as we go from reactants to products, we have to put heat into the system. And that's why the temperature of the surroundings decreases, because the surroundings will be giving some of its heat to the system. So this is, again, positive delta H for endothermic. So we don't in reality measure usually the absolute enthalpy of the reactants, the absolute enthalpy of the products, and subtract them in this way. But that's in reality what it means when you have a negative or a positive delta H. So that's just one less conceptual look at kind of a little bit about what delta H means, and what we're kind of defining as the initial and final state in a reaction is always reactants are the initial state, products are the final state. Differences in enthalpy between those two gives us the non-zero delta H terms that we can usually have. All right, so that's just one last aspect of background. So any questions on sort of the conceptual aspects of enthalpy? Okay, the biggest thing you're going to have to do in this section of the course is problems that involve calculating heat or calculating delta H and relating those two to each other. So that's what we're going to get into now, is the more quantitative aspects of things, which is going to be a big part of what you have on the homework assignments and exams. So let's talk about how to calculate heat. We talked about how to calculate work earlier for one specific situation, but for heat, this different equation. It applies to any situation where there's a transfer of heat between the system and the surroundings. So first, let's build up a proportionality. And then let's just think about this a little bit as a thought experiment. All right, so let's imagine we're trying to warm up some water, okay? So we're going from like room temperature almost to the boiling point of the water. We're heating up the water. So if this shouldn't be, don't overthink this one. I'm not trying to trick you guys. So if you have a little bit of water versus a huge pot of water, so if you have more water, is it going to require more heat to warm it up or less heat to warm it up? Okay, good. Yeah, don't overthink it. So heat is proportional to the mass of the substance. So when we have heat transferring between systems and surroundings, and if we know the mass of our system that we're measuring, the more mass it has, the more heat would have to go into it for that same temperature change. And then the other thing is, let's say we have now the same two containers of water, same exact volume of water, or mass of water, and one of them we're going to heat up just a little bit, like a few degrees, and one of them we're going to heat up all the way to the boiling point. So if you heat it up, so if you have a bigger temperature change, is that going to be more heat going in or less heat going in? More, good. So that means heat is also proportional to the change in temperature. The bigger the change in temperature, the more heat was involved in that process. So heat is proportional to two things, and a mathematical trick that I don't know if we've talked about yet, but we're going to also use it in Chapter 8, is that if one term is directly proportional to two different things, it's also proportional to the product of those two things. So we can also write that the heat is proportional to the mass times the change in temperature. Okay? And something else we may have seen once before, but we'll definitely see it again in Chapter 8 also, is that if you have a proportionality sign, meaning it's proportional to those two but not exactly equal to those two, if we want to change this to an equal sign, we just have to put a constant on one side of the equation. And so the constant that we use is going to be abbreviated as lowercase c, another lowercase c, but not speed of light in this case, unfortunately. But it's going to be mc delta t, where c means something different here. But this is going to be the equation for heat. The mass of the substance, the change in temperature that it undergoes, and then this constant here, c. So let's talk about what this specific heat capacity is. That's what lowercase c represents. So c represents the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. That's usually the units that we put it into. It's the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? Now, one thing I want to start bringing up here, because it's often a source of confusion in this chapter, and then especially as we compare to what happens in chapter 8. So if we're talking about here, this is always a delta T, a difference in temperature that we're talking about. So the delta T is going to be the same whether it's in Celsius or Kelvin. Okay? The absolute temperatures for Celsius and Kelvin are different. The temperature in the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. So the absolute temperature is different, but delta T is the same because the size of 1 degree is the same whether it's Celsius or Kelvin. So don't be confused with that. Whenever we're talking about delta T, it doesn't matter if you use Celsius or Kelvin, the difference in those two temperatures will be the same as long as you're subtracting the same units. So you might see it also written in Kelvin. So every substance has a different specific heat capacity. So it is dependent on what substance you are. It's not a universal constant. It's specific to each substance. The one that we're going to use the most, and the one that you should definitely be familiar with, is water, which has a specific heat capacity of 4.184 joules per gram degree Celsius. Or you might see it as same number, 4.184 joules per gram Kelvin, because it's, again, based on the change in temperature delta T. So Celsius or Kelvin are equivalent in that case if you're talking about a difference, a range of temperatures. Okay? So that's the heat equation. Really, anytime you're asked to calculate heat, you immediately want to think about mc delta T. That's really the equation that we'll have for calculating the heat involved in any sort of physical or chemical process. Now there's one more heat capacity that is sometimes used, but not nearly as often, but we should be a little bit familiar with it, or just introduced at least, which is called molar heat capacity. So as the name implies, so specific heat capacity is in terms of grams of substance, molar heat capacity is in terms of moles of substance. So it would be the amount of heat needed to raise the temperature of 1 mole of substance by 1 degree Celsius. It's not used nearly as often because the standard equation for heat is in grams, in mass of substance, not in moles. But sometimes you may come across this, so I just want to make sure you're familiar. So you're raising the temperature of 1 mole of substance by 1 Kelvin or 1 degree Celsius. And that amount of heat would be termed the molar heat capacity. And because the powers that be just like to be as obtuse and confusing as possible, it's also abbreviated with C, although usually it's a capital C. The units will give it away because it'll be per mole instead of per gram. But it is also abbreviated often with capital C, just to drive people crazy, I suppose. I'll change that if I ever take over the world, but not yet. All right, so that's going to be capital C for molar heat capacity. The nice thing is, because we know the relationship between grams and moles, we can always calculate one from the other. If we're given a specific heat capacity and we need the molar heat capacity, we can calculate it, or vice versa. So as an example, if we want to do it for water, we told you on the last slide that the specific heat capacity for water is 4.184 joules per gram degree Celsius. So if we want to do this per mole instead of per gram, we just need to convert grams into moles. And so for water, I'm not going to calculate it in detail, but the molar mass of water is 18.02 grams per mole. So if we put grams up here to cancel out and moles in the bottom, we multiply by that. So 18.02 grams in 1 mole. That's the molar mass of water. So grams cancels out. That leaves us moles down here. And so just multiplying those two gives us the molar heat capacity of 75.40 joules per mole degree Celsius. All right, so the only difference between these is whether it's per gram or per mole. And they're going to be related by the molar mass, just the simple relationship for mass and moles that we've already covered many times. All right, but again, you will not likely encounter that very much at all, but I just wanted you to be familiar with it in case it does come up. All right, so now that we have the equation, let's go through then different situations of how we would use it, because it's really just one equation, but different contexts and different scenarios that we want to be familiar with. All right, so this is a pretty straightforward one. We have an aqueous chemical reaction conducted in 50 milliliters of water. The temperature raises from 22.31 degrees Celsius to 28.37 degrees Celsius. Determine the heat absorbed by the water. So what we're working towards here is how we can use heat to measure delta H for a chemical reaction. We're not quite there yet, but this is essentially how we do it. We run the chemical reaction and we measure the change in temperature, and those two things together can help us find what the heat would be. So whenever we're calculating heat, we want to think of MC delta T. Now the important thing here is that the mass that we put in is the mass of the substance that absorbs all that heat, or that gives off the heat if it's an endothermic process. So here we're saying that there's 50 milliliters of water present. So all that water is going to absorb the heat that's produced by this reaction. So we'll need the mass of water, we'll need its heat capacity, since that's again what's absorbing the heat, and the change in temperature delta T. And so in problems like this, very often some of these terms are going to easily be given to you in the problem. So the mass of water is 50 milliliters. This is one thing we need to cover a little bit right now, because in many cases, water is a liquid, is measured in terms of volume, not in terms of mass, but we have to be able to relate the two. But it's very simple for water. So the relationship between mass and volume is density, which we would have had in the review chapter a long time ago. So if we want to find the mass of water that corresponds to 50 milliliters, we just need to use the density. So grams on the top, milliliters on the bottom, that's the density of water. The nice thing is the density of water is what in this unit? So it's the only density you should memorize. 1, good. So if you can memorize the number 1, you're good to go in the density of water. So that's the density of water. So in reality, the mass in milliliters, the mass in grams, the volume in milliliters are the same number for water. So you don't have to even do this conversion explicitly. So it's going to be 50 grams. So you don't have to do that conversion, you can do it in your head, but that's how we're getting from 50 milliliters to 50 grams for the water that's present. So that's the mass of our water. The heat capacity of water, I think we'll usually give it to you, but you should probably just learn it to be safe. You're going to use it over and over again anyway, so if you're paying attention while you're doing the problems, you will learn it without trying. So that's the heat capacity of water, 4.184. That's joules per gram degree Celsius. And then finally, we need the delta T term. So delta always means final minus initial. So in a lot of cases, you'll have to calculate that, but it's very simple. It's just subtracting two numbers. So you have to look closely at which one's final and which one's initial to get the sign right. But it's going from 22.31 to 28.37. So that's our final, and that's our initial. And so we're just going to subtract those two numbers. 28.37 minus 22.31. 6.06 degrees Celsius, positive number because the temperature is increasing. All right, so that's going to be our delta T, 6.06 degrees Celsius. So now we just need to multiply three numbers together, 50, 4.184, 6.06, and that gives us the number in joules, because our heat capacity is in joules, 1268. We didn't specify units in this problem, but very often in chemistry context, we'll want it actually in kilojoules instead of joules. It's just a more common unit for chemistry, so we have to divide this by 1,000 if we ask for kilojoules. I guess we're probably carrying one extra sig fig, but that's okay. So I don't think I specified it in this problem, but more often kilojoules than joules, but just, again, look closely at what we're asking for. It's just dividing by 1,000. All right, so any questions on that one? That's just straightforward application of MC delta T. All right, now the other way that we can use this specific heat, we have that one equation, so of course we could have something else that's unknown besides the Q term. So let's go back to one of my favorite elements, gold. So if we have a 1 ounce gold coin and it absorbs 721 joules of heat, by how much does its temperature increase? So again, if you're talking about heat, there's really only one equation we have to worry about, which is MC delta T. The only difference here is that our unknown is going to be delta T. All right, this problem, we're telling you how much heat we're putting in. We're giving you the specific heat capacity, which is now much different because it's a metal and not water anymore. Metals typically have very low specific heat capacities. And then we're giving you the mass, which is related, given in ounces, but then related to grams. So all we're doing here is just solving for a different term, delta T, so it just requires a little bit of algebra to solve for that. All right, so we can set things up a little bit differently, but it's really just the same relationship. So now we just have to plug in the terms. The Q, it's absorbing 721, so that means, and then this is where we have to pay attention to terminology a little bit. Absorb, that means that Q is positive, right? Because our delta T could be positive or negative depending on whether the heat is absorbed or released. Absorbing means that Q is positive, so we don't want to put any negative sign in front. That's just 721 joules is Q, positive number. And then the mass is 28.35 grams. It's 1 ounce, but we want it in grams because that's what specific heat capacity is in. And then the C here, different now because we're not water anymore. Water is the only one that you should know. And that's going to be 0.129 joules per either Kelvin or gram degree Celsius. So when we divide this out, we get 197 degrees Celsius. So putting in 721 joules into a 1 ounce gold coin would raise the temperature by a huge amount. 197 degrees Celsius would be the delta T, the amount that it changes by. All right, so that's again just another application of that same relationship, just solving for something different. All right, any questions on that or this equation? All right, but let's now get into what we're really going to most often use this equation for, which is an experiment called calorimetry, which, here we are, which I never know what you guys do in the labs, and I feel bad about that, but then I never take steps to fix that lack of understanding on my part. I don't know if you guys do a calorimetry experiment in the chem lab or not, but it's, it's an experiment that allows you to measure heat. So basically a calorimeter is a device that's used to measure heat. And we've already talked about, well, all you need to measure heat is the mass of the substance and the change in temperature. Why do we need a fancy device? Well, the reason is because remember that whenever we're having heat transfer in a chemical reaction or a physical process, heat is transferred from the system to the surroundings, and in reality the surroundings is the whole rest of the universe. So what a calorimeter does is it basically isolates your surroundings, keeps it nice and contained, insulated if you will, so that you don't have to worry about the heat just dissipating everywhere, and you can contain it and measure it more easily. So the calorimeter contains the surroundings. So that the heat that's released to the surroundings is in a nice contained area, not dissipating through the whole room, through the whole world. And usually a calorimeter is filled with water. Water is most often the substance that would absorb that heat. And then the calorimeter itself is going to be insulated so that the heat that gets absorbed by the water does not then get transferred out into the air, into the surroundings around that. So it's an insulated container with water in the inside. So when we have a calorimetry problem, there's different contexts that we can use in. The two main contexts for calorimetry are either measuring a specific heat capacity of a substance or measuring a delta H or delta E for a chemical reaction. But the equations that we start with are the same in either situation. And so the first thing we're going to want to do is determine what I'll abbreviate here as Qcal. This is the heat absorbed or released by a calorimeter. And there's three possible scenarios depending on the information we're giving you and in a laboratory setting depending on how precise you want to be. So in some situations, all we do is give you the amount of water in the calorimeter. We just say a calorimeter is filled with this much water, and that's all you know about the calorimeter. And so in that case, the way that we would calculate heat is just one term. The heat for the calorimeter is just the heat that's absorbed or released by the water, which is just mc delta T, one term. And so if you only have the amount of water, we know the heat capacity of water is 4.184. That doesn't change in a calorimeter. And so that's the only thing you need. That equation plus this heat capacity we've already talked about, 4.184. Now, in reality, if you're talking about this in an experimental setting, this is not the most precise way to do a measurement in a calorimeter, because you're assuming that all of the heat is absorbed by the water. But like, there's also the container, the calorimeter's container, the thermometer itself absorbs some of the heat. So you're not accounting for everything if you're just saying all the heat's absorbed by the water. That's an approximation, but would lead to, you know, some error in your measurement. The other possibility is that in some cases, all we do is give you the heat capacity, capital C, of the calorimeter. We don't tell you how much water's in there. We just give you a single heat capacity value that includes everything. It includes the water, it includes the materials of the calorimeter. It's just a constant for that calorimeter without specifying how much water there is. And so in this case, it's also just one term. And this heat capacity here is going to be in units typically of joules or kilojoules per degree Celsius. It's not a specific heat, it's not per mass of substance or anything like that. It's just a total heat capacity for the whole thing, whatever's in there. And so in that case, the heat is just a product of those two terms, C calorimeter delta T. So this would, in some sense, be the easiest situation because you're only multiplying two things together to get the heat for the calorimeter. Okay, so that would be a situation where we just combine everything into one big term. It's just a single heat capacity in joules per degree Celsius. You don't know how much water is in the calorimeter. You don't know anything else except for a heat capacity term, and that's all you need. Now, the last situation is we give you both of these pieces of information. So we'll tell you how much water is in the calorimeter, and we'll tell you the heat capacity of the empty calorimeter, so the calorimeter that doesn't have water in it. And in that case, you have to add those two terms together. So the heat for your calorimeter would be the heat capacity of the calorimeter times delta T. That's the amount of heat absorbed by the calorimeter itself, plus mc delta T, the amount of that's absorbed by the water. So in reality, these are the two terms that we would need to calculate the heat absorbed by a calorimeter, but depending on how the problem is set up, sometimes you will explicitly add those two terms together. In other cases, we'll either ignore the heat capacity of the calorimeter, or we'll just group everything together as we did in scenario 2. So you really just have to look closely at what the problem is giving you. If you have the mass of water in the calorimeter, you know there's going to be an mc delta T term. And then if you also have the heat capacity of the calorimeter itself without the water in it, the empty calorimeter, then you're going to have this term as well. The heat. So just again, look closely at what the problem is giving you to know how we calculate the heat for the calorimeter. It's going to be one of these three situations in every case. All right, so it's no more than two terms. Sometimes it's only one term, but you have to read closely to figure out the way you want to approach that. All right, so that'll make more sense as we do some examples. But let's talk then about what a calorimeter looks like a little bit. So again, it's a device that's used to measure heat, as we defined on the last slide, and it contains the surroundings. So the first type of calorimeter we'll talk about is what's called a constant pressure calorimeter. And in a very simple laboratory setting, it could just be, you know, coffee cups basically, or maybe two coffee cups stacked on top of each other that's used as your insulating material. So it doesn't have to be anything super fancy. And so what you have in here is in the inner coffee cup, that's where you have your reaction, usually an aqueous reaction for these types of things, because it's just a cup of water where the reaction is happening. And then you're going to have a thermometer, and then something to stir the reaction, and some sort of cap that insulates things as best as possible. But this is not like a tightly sealed system, so it can vent pressure to the surroundings. The pressure is going to remain constant during this, because it's not totally open. You want to contain it as best you can, but it's also it's also vented, so it's not going to build up pressure. So a constant pressure calorimeter is vented, and it's going to be most useful for processes occurring in either the liquid or solid phase. We'll talk about another kind of calorimeter next time, which the math doesn't really change, but if you're talking about like measuring a combustion reaction, which is commonly done in calorimetry, you can't measure a combustion reaction here. You can't burn something in water. And if you released all the CO2, it would just go everywhere because it's vented and all that stuff. So this would be terrible for doing a combustion reaction. But for simple, chemical reactions, or for just transferring heat between, water and an object, then this is totally fine. So the first application of calorimetry we're going to talk about is determining an unknown specific heat capacity. So that value of C that we have, 4.184 for water, what if we have a new material, we're trying to measure that heat capacity? How do we do that? Well, we can use a calorimeter for that. So the way that this works is that you would heat up the solid. So you do it for an insoluble solid, something that you can just place in the water, and it'll transfer heat, but it's not going to dissolve or it's not going to react with anything. So you'll take your solid, like a piece of metal, for example, you'll heat it up to some temperature. A convenient temperature is 100 degrees Celsius because you can just put it in boiling water to get it to that temperature. And then you drop it into the calorimeter that has colder water in the middle. So you're going to place it in cold water in a calorimeter, that hot object that you've heated up. And so then what happens is, remember, we talked about heat transfer is just whenever you have two things that are different temperatures, they're going to transfer heat between them. And that's what's going to happen when you put a hot piece of metal inside of cold water in a calorimeter. It's going to transfer heat to the water. And so what you'll have is you're going to measure the initial temperature for both, which are going to be different from each other. So you need to know the initial temperature of both things. And then you're also going to measure the final temperature, which will be the same for both, because the heat is going to stop transferring when they get to that same final temperature. So you measure basically three temperatures: the initial temperature of the hot object, the initial temperature of the water that you're putting it into, and the final temperature, which would be the final temperature that both of them reach once the heat is no longer being transferred. All right, and so then what happens here is you treat your solid as the system and the water as the surroundings, or vice versa, and so heat is transferred between the two, and in magnitude they're the same, but in sign they're different. So what you have is, let me do this most logical way. So the heat for the solid is equal and opposite to the heat for the water. You can put the negative sign on either side of the equation and it works. But basically those two heat terms are identical in magnitude. Whatever heat is lost by the metal is going to be gained by the water. So there's no creation or destruction of heat. It's just going to be a transfer between the two. So they're equal in magnitude, opposite in sign, not mass, Q. Sorry, I'm getting ahead of myself. And then then what you can say is, using MC delta T on both sides, the heat for the water is the mass times C to delta T, and it's the same for the solid. I'm all over the place, sorry. So long story short, you're going to do Q equals MC delta T, both for the piece of metal that you put in and for the water that absorbs the heat. You set those two equal to each other but opposite in sign. And then you solve for whatever your unknown is, which is usually going to be the heat capacity of your solid. Okay, so if we wanted to solve for that algebraically, we could, but we're basically going to just use this relationship here. And then you're going to set them equal to each other and solve for your unknown, usually, which is your heat capacity. Now, the only thing to be aware of that we already talked about a little bit is that sometimes for the calorimeter, you're going to have a second term on this side, which is the heat capacity of the calorimeter in delta T. If we give you both of those, you still need to account for that, because in that situation, whatever heat is lost by that piece of metal is going to be absorbed both by the water and the calorimeter, and you have to account for that. So again, it just depends on the information that we're giving you. All right, so this is going to make more sense when we do example problems. So let's go through one. So we have 10 grams of a solid. We heat it to 75 degrees Celsius and then place it into a calorimeter that contains 50 grams of water initially at 25 degrees Celsius. So we have the initial temperature of both. Sorry. We have the initial temperature of the solid, the initial temperature of the water. So then heat is going to be transferred between them, and we measure a final temperature of 26.64 degrees Celsius. What is the specific heat capacity of the solid? Okay, so this is going to be, a very straightforward, very typical type of problem, finding a known specific heat, C here for the solid. Now, in reality, what we have to do is we have to first think about, what terms do we need to calculate the heat for the calorimeter, which again is going to be the mass of the water in the calorimeter, heat capacity of water, its delta T, just call it a single delta T term, plus the heat capacity of the calorimeter times delta T. So in knowing which of these terms we need to use, we again have to look at the information in the problem. So are we telling you in this problem what the overall heat capacity of the calorimeter is? Did anybody find that anywhere? No, I see some head shaking. So we don't know anything about this term, so that one's out. We are telling you, though, how much water is in the calorimeter. We know the heat capacity of water, and of course we have the delta T. So this is how we're going to calculate the heat for the calorimeter. All right? And then as we said on the last slide in slightly different terms, the heat for the solid, or the metal that we're putting in, is going to be equal and opposite to the heat for the calorimeter. So we're going to basically set those two equal to each other, just like we talked about. So we're going to have MC delta T on both sides, the mass of the solid, the heat capacity, which is what we're solving for, and its delta T. Then we're going to put a negative sign out front. We're going to have the mass of the water, heat capacity of water, and its delta T. Because again, in this case, we're assuming that all the heat is absorbed by the water. We're not giving you any information about the heat capacity of the calorimeter. So now we're ready to solve for our unknown. So let's just start plugging in some numbers. And what we first also need are the delta T terms, but let's write in what we have so far. So the mass of the solid is 10 grams. So we have a 10 gram piece of solid. Heat capacity of the solid is what we're solving for, so that's our unknown. And then for the delta T of the solid, we have to, again, do final minus initial. So the final temperature for both is 26.64 degrees Celsius. So that's our final temperature. That's when the heat is no longer transferring. And the initial temperature for the solid is 75 degrees Celsius. Okay, because that's where it was starting out at a higher temperature. So the delta T for the solid is minus 48.36 degrees Celsius. We'll keep some extra sig figs for now. So that's our delta T for the solid, minus 48.36. And then we're going to set that equal to MC delta T for water, but with a minus sign up front because the two signs for the heat have to be opposite each other. So the mass of water is 50 grams. That's directly given to us. Heat capacity of water is always known, 4.184. And then delta T for the water, same final temperature of 26.64. They both go to the same final temperature. The initial temperature for water was 25.0. So the water is warming up because it's absorbing the heat from the solid. And so that's going to be a positive 1.64. So that goes in here. All right, so now we just have to multiply, divide, and get heat capacity of our solid. So we do some algebra and find that the heat capacity of the solid should be 0.709 joules per gram degree Celsius. Okay, so it's just setting up MC delta T for both things. Put a minus sign on one side, doesn't matter which side of the equation the minus sign is on, and then solve for your unknown, which in this case is the heat capacity. All right, so any questions on that? All right, the other major application of calorimetry is determining delta H. We just defined it today, so we'll give a quick reminder of the definition of that. Where does this start? Oh, come on. Here we go. All right, so we have to do a quick reminder of the definition of delta H. So delta H we saw earlier was delta E plus P delta V, which is equal to the heat measured at constant pressure. So we can directly measure delta H in a constant volume calorimeter, constant pressure calorimeter, by just measuring the heat associated with that. All right. And so we're going to do these two steps. It's going to be a little bit different, but really the same concept. The reaction occurs in the calorimeter. If it's exothermic, it releases heat to the calorimeter, and the temperature of the water inside the calorimeter goes up. If it's endothermic, it absorbs heat from the calorimeter, and the temperature goes down. So we're going to measure the temperature change of the calorimeter contents. We know what's in the calorimeter, the water, the contents, all that stuff. And so we're going to calculate the heat for the calorimeter the same way we've already introduced. QCal, as we abbreviated it, is mass of water, heat capacity of water, times delta T. And then we also have, so this is again the heat that's absorbed by the water. Then we also have the heat capacity of the calorimeter itself times delta T. And depending on what information we give you in the problem, you're going to either use one of these terms or both of these terms. It really just depends on how it's set up. But those are the two things we need to calculate the heat for the calorimeter. In this case, though, we're not measuring MC delta T for the reaction. We're trying to measure delta H. And the way that this works is we'll say that the heat of the reaction, QRXN, heat of reaction, is equal and opposite to the heat for the calorimeter. Again, minus sign on either side in reality. But this is just measuring the heat involved with that reaction at the specific scale that we did it on. So this value like if we did a combustion reaction of, let's say, gasoline in a calorimeter, if we burned like 1 drop of gasoline, that's going to release a little bit of heat. If we burned, a gallon of gasoline, that's going to release a ton of heat. So the amount of heat that we measure depends on how much reactant we're using for that process. So it's not a very useful number on its own. What we're really interested in is the delta H for the balanced chemical equation itself. So the way that we have to do this then is to actually get delta H for the reaction. We're going to take the heat of reaction and divide it by moles of substance. Usually it's going to be, the moles of what, most often situations, if we're doing like a combustion reaction, it'll be the moles of substance that we're burning. So how many moles of gasoline do we burn? Gasoline's a mixture, so you can't really define that, but nonetheless, this is how you would do it. Heat of reaction divided by moles of substance. So that's how we kind of normalize it and, get an actual useful value for delta H, because the amount of heat that we get is going to depend on how big of a reaction we're doing. All right, but let's talk about then how to do this with some real examples. So first one we're going to do is heat of solution. So we talked about earlier that sometimes when you dissolve things in water, the temperature of the water increases or decreases. It can be an endothermic or exothermic process just for dissolving. So ammonium chloride is one of those. So we have 1 gram of ammonium chloride added to a calorimeter with 50 milliliters of water. Initial temperature 22.3 degrees Celsius. If the final temperature is 20.98 degrees Celsius, what is the enthalpy of dissolution in kilojoules per mole? We're assuming that the density is 1.0 grams per milliliter, and we have the same specific heat capacity as water. Because the reality is we are dissolving something in water, so the density of the solution is not going to be exactly 1, heat capacity is not going to be exactly this, but it's going to be close, so we're just going to make that assumption. So what we're doing here is, again, we're just doing dissolving an ionic compound. Ammonium chloride as a solid, adding it to water, and making aqueous ammonium chloride. And we're trying to find what the delta H is for that process. So dissolving 1 mole of ammonium chloride in water, what's our delta H, or change in enthalpy? So we're going to follow the steps that we just learned, and so we're going to do heat for the calorimeter is going to be the mass of the water, heat capacity of water, times delta T, plus the overall heat capacity of the calorimeter times delta T. It's going to be one or both of those two terms. This is another one like the last one where we're telling you how much water is in the calorimeter. We gave it as milliliters, but 50 milliliters is the same as 50 grams. We did not give you a heat capacity for the calorimeter. There is no information in this problem that tells us the heat capacity of the calorimeter is some value. So just like the last one, we're going to just assume that all of the heat is absorbed by water and ignore this term here. So we're just going to say that the heat absorbed by the calorimeter all goes into the water, in which case it's just MC delta T. Now, one of the common mistakes that people make in calorimetry problems that you should be aware of is the mass that we want to use here is the mass of the water that's absorbing the heat, not the mass of the substance that's involved in the reaction there. Okay, so when we do a reaction in a calorimeter, there's going to be masses of substances involved, but all the heat that's produced, we're going to assume is absorbed by the water. So we don't want to use this mass here in calculating the heat. This mass will come into play later, as we'll see, but it's not going to be used for determining heat. The only mass that matters for calculating heat is the mass of the water in the calorimeter, if we're doing a chemical reaction specifically. So we can calculate that now with the information we have. So the mass of water is 50 grams. Heat capacity of water is 4.184. And again, we're assuming that the heat capacity is not changing even though we're dissolving something. And then delta T, we have to calculate again, but same thing as last time. Final minus initial. So the final temperature is 20.98. Initial temperature was 22.3. So our delta T in this case is negative 1.32 degrees Celsius. All right, so that's going to be a negative heat term of minus 276. All right, so the temperature of the calorimeter decreased, which tells us that it's an endothermic reaction, and this is the value we get for the heat for the calorimeter. But what we're interested in is not the heat for the calorimeter, but the heat for this reaction or this dissolution process here. So that's going to be negative heat of the calorimeter, which is plus 276. All right, so if heat for the calorimeter is negative 276, heat for the reaction that occurred inside of that was plus 276. And then what we're left with is to find the delta H. So delta H is going to be heat of reaction divided by the moles of substance. In this case, we're dissolving ammonium chloride, so that's going to be the substance that we're interested in, so we're going to divide those two. Okay, because this is the amount of heat when we dissolve 1 gram of ammonium chloride, but what we're looking for is the amount of heat when we dissolve 1 mole. We want it in kilojoules per mole, which is the most common way that we do it. So we have to convert grams to moles and divide the two. So we have 276 joules is the heat, and we're going to divide that by the moles of substance that we dissolved. Well, we know how to calculate moles by now, I think. So we're going to say the moles of ammonium chloride is 1 gram divided by the molar mass. So 1 mole of ammonium chloride, and we gave you the molar mass, I believe. Yes, 53.49, so we don't have to calculate that. So if we divide the mass by the molar mass, we get 0.0187 moles. So if we want to find delta H per mole, we have to take the heat that we measured and divide it by the moles of substance that we dissolved, which is 0.0187. We want it in kilojoules, so we're also going to do a conversion of 1 kilojoules is 1,000 joules, divide by 1,000. And so what we end up with is a positive number, 14.8 kilojoules per mole. So you absorb 14.8 kilojoules when you dissolve 1 mole of ammonium chloride. All right, so that's going to be how we would use this to measure it. So you measure the heat for the calorimeter, calculate it in this case, and then you relate that to the heat of reaction. So the key difference here is in the first problem we did, we were measuring a specific heat capacity of a substance that wasn't reacting, it wasn't dissolving, it was just transferring heat to the water. So there we had to use MC delta T for the substance as well to solve for its heat capacity. Here we're doing not really a chemical reaction, but a process on ammonium chloride. And so the only place the mass comes in is to figure out how much substance we have. In this case, in moles is what we want. So we use that to normalize our delta H to the amount of substance, 1 mole, that we're interested in. Okay, so make sure we, again, you have to do a lot of different problems like this to get familiar with the different situations, but make sure you're not using these mass terms incorrectly, which is a common mistake people make. All right, any other questions on that one? Yeah.
Why did it turn to a positive 276?
So it turned to a positive because whenever you have any process happening in a calorimeter, whether it's a physical or a chemical process, the heat for the calorimeter is going to be opposite in sign to the heat for the process you're measuring. So we got a negative number for the calorimeter because delta T was negative, and so then the heat for the reaction or whatever we're studying is going to be now a positive number. So it's just that step there. Got it to positive. Anything else? All right, let's do another similar one. This one's pretty annoying, but we'll do it anyway. So we have 50 milliliters of 1 molar HCl in a constant pressure calorimeter, and we add 1.60 grams of solid sodium hydroxide, and the temperature increases by 7.27 degrees Celsius. What is the heat of reaction in kilojoules per mole of water formed? Assume the density is 1 and assume the heat capacity is still 4.184. Okay, so this is an acid-base reaction this time. So we have HCl, which is an acid, NaOH, which is a base. We should immediately recognize that from chapter 6. So acid plus base reacts to make water plus ionic compound, as we already talked about. Okay, so this is the reaction that's happening. HCl plus NaOH making water and sodium chloride. And so the first step is going to still be the same. We're going to find the heat of the calorimeter, which is just going to be MC delta T for water plus heat capacity of the calorimeter times delta T. Again, we didn't give you the heat capacity for the calorimeter in this one either, so we're going to ignore that term. We will have some next time where that comes into play, so don't think it's always gone, but we just need MC delta T again for the calorimeter. And we see in this problem that we didn't specifically tell you how much water is in there, but we have 50 milliliters of an aqueous solution of HCl. So when you have an aqueous solution, that's going to be mostly water. So again, we're going to assume that we have 50 milliliters of water with a density of 1. Not a perfect assumption, but that's the amount we have. So we're looking for how much water is in the calorimeter because that's going to be what's absorbing the heat. And the aqueous solution of HCl is made up of HCl dissolved in water, so we're going to use that number 50 as the amount of water that we have. So 50 grams of water. The heat capacity, again, we're still assuming is 4.184, even though we're dissolving things in it. And then delta T increases by 7.27 degrees Celsius. So it's going to be a positive 7.27 degrees Celsius for delta T. We have to calculate it here. So that gives us 1521 joules. So the heat of our reaction is, the heat for our calorimeter is 1521, which means that the heat for the reaction is the negative of that. Let me write it out more explicitly. Negative heat for the calorimeter, which is negative 1521. All right, because again, the heat that is lost or gained from the reaction will be gained or lost by the water. So if our heat for the calorimeter, heat for the water is 1521, heat for reaction is minus 1521. But that's for this specific scale. We're looking for the delta H in kilojoules per mole of water formed. So if we want to find delta H, what we have to do is take that heat of reaction and divide it by the moles of water that are formed. So the annoying thing about this problem is to figure out how much water is formed, we have to do stoichiometry, because we're giving you the amounts of each reactant, HCl and NaOH, but we want to find the delta H in terms of the moles of water that are formed, which we don't have directly. So we have to calculate that using stoichiometry. All right, so what we're going to do is find the moles of each reactant first. So for HCl, we have a 50 milliliter solution. So this is a little bit of a review of chapter 6. So I guess it's not terrible to have it here since that exam is coming up soon. So we have 50 milliliters of HCl solution. The molarity is 1, so we have 1 mole of HCl per 1 liter, or 1,000 milliliters. So this is a review of solution stoichiometry that we just covered on Tuesday. So we have 0.0500 moles of HCl. For NaOH, we did it in mass, 1.6 grams. So we're going to use the molar mass of NaOH to calculate the moles of NaOH, 40 grams per mole. So this molecular weight there is 40.0, so that we're going to divide by that. So we have 0.04. So technically this is a limiting reagent problem because we have amounts of both reactants, HCl and NaOH. This one we can do in our head because all the coefficients are 1. So this number is smaller, so that's going to be our limiting reactant. There's fewer moles of that. They all have coefficients of 1. So if we have 0.04 moles of NaOH, we're going to also form 0.04 moles of water. Okay? This is a 1-to-1 reaction, so whichever one of these is smaller is going to limit how much product is formed. 0.04, that's going to be the amount of water that we get. So we're going to divide those two. So we have heat of reaction is negative 1521 joules. The amount of water that's formed is 0.04 because that's the amount of limiting reactant we have, and it's a 1-to-1 reaction. And then we're going to convert to kilojoules, same way, divide by 1,000. Do it in one step. So we get minus 38.0 kilojoules per mole. It's not going to be particularly common that you have to combine calorimetry and stoichiometry like this. I just gave this one as kind of a more involved example to show you some of the different steps that go into this, but this was a good review of what we learned today, calorimetry, as well as the stoichiometry stuff that we covered last time. I'm going to skip this last one because that's like 3 steps and I don't want to rush through it. So I'll cover this one next time. I encourage you to try it on your own before then and see if you've picked up the things that we've learned today. So I will stop there and we'll pick up on other aspects of calorimetry and delta H starting next week. Okay.